In this video, we're going to look at higher order partial derivatives. All right, so we know from Calculus 1 that once we have the first derivative, we can then differentiate that and get the second derivative, and then differentiate that and get the third derivative, and so on. And so we're going to apply basically the same logic to partial derivatives. So if I have a function, z equals f of xy, then we can compute the two partial derivatives, which I'll call f, in this case, f sub x and f sub y. And these are both functions of two variables themselves. Right? And so these are functions of two variables, and so we can differentiate each of those with respect to whichever variable that we want. And so we actually end up with four possible what are called second order partial derivatives. Right, so in this case, what we could do if we took function f, if we took the partial with respect to x, f sub x, and we differentiated that with respect to x, right? We could do that. We could also take f of x, f sub x, and differentiate it with respect to y. And then we could do the same thing for f sub y. We could first differentiate it with respect to x, and then differentiate it with respect to y. And that produces, at least on the surface, four different derivative functions. And so right now I want to go through just quickly and point out the different notations for these. Just like with the first derivative, there's a bunch of notations for each of these. And there is one thing about this notation that's a little bit confusing, which I'll point out at the end. So instead of writing this like f sub x and then outside of parentheses another sub x, a lot of times we will just write f sub xx. So a subscript with two variables in a row like this to indicate that we're differentiating with respect to x twice. Right? Now we could also write this as del x of f sub x. This is another common notation that we're differentiating the partial f sub x with respect to x again. Sometimes we write this as del squared of f over del x squared. Right, so this is sort of the analogous thing to the d squared y over dx squared notation from Calc 1 for the second derivative. We might also, instead of f, we might also have a z here, so del squared z over del x squared. Right, and we might also denote this by z sub xx. So again, the double subscript denoting that we're differentiating with respect to x twice. Now I'm going to jump down to f sub y now, and I'll just go through these really quickly because it's exactly what we just did for fxx, except everything is in terms of y. So those are analogous. And it's the two in the middle where the notation becomes a little bit confusing. Right? So when we want to get rid of the parentheses here, if we sort of keep the subscripts as they are, we might label this as f of xy. And this is what we're going to do. So f of xy is the derivative that we get by taking f, starting with f, differentiating with respect to x first, and then y. So in this case, that's the order. The first exponent is what we differentiate with first. The first subscript is what we differentiate with first. The second subscript, what we differentiate with second. Right? And so this would be del y. So we're differentiating f sub x with respect to y. But this is when it gets confusing, because now it's going to be del squared f del y del x. So notice now the y and x are in the opposite order. So when we have the subscript notation with the f sub xy, the variables are going from left to right in order that we're differentiating by them. But the del f del x kind of notation, we're thinking of that as more of an operator. So like we did in this previous item here, where we're thinking of taking the derivative of x first and then multiplying on the left by del y. Right? And of course, same thing works for z, del squared z over del y del x. And the last notation z, we go back to the left to right notation in zxy. Right? And so the third row is virtually the same, just everything is reversed. So f of yx, now we're doing del x of fy. Right? This is going to be del squared f over del x del y, or del squared z over del x del y, and zyx. Right? So I know there's a lot of notation here, but what I really wanted to point out was this the middle two when we have the middle two derivatives, which I'll also point out here. These two here are called the mixed partial derivatives. For obvious reasons, they're the partial derivatives that mix x and y together. So that's just when we refer to mixed partial derivatives, we're talking about the ones with both x and y. All right, so let's take a look at an example. All right, so let's say we had the function f of xy equals x sine y minus e to the xy squared. So that xy squared is in the exponent of the exponential function. Right? And I want to find all the second order partial derivatives. So that means I want to find all four of the partial derivatives that after differentiating twice. Right? And so to do that, the first thing I need to do is find the first order partial derivatives. Right? So f sub x, I'll leave out the xy notation. We know we have functions here. So if I differentiate with respect to x, I'm going to get 1 times sine y minus the derivative of the exponential function. We always have the function itself multiplied by the derivative of the exponent. And so that exponent, the derivative of xy squared, is going to be y squared. So this is just going to be negative y squared e to the xy squared. Okay. And also we're going to, if we differentiate with respect to y, we're going to get x cosine y. Right? X is a constant there. Minus 2xy, that's the derivative of the exponent xy squared, times e to the xy squared. Right? And so these are our two first order partial derivatives. And now to find our second order, we're going to just differentiate each of these with respect to each variable. So if I want to find fxx, the partial with respect to x twice, we're going to differentiate f sub x with respect to x. So when we differentiate sine y, that becomes 0. When we differentiate the second term, we're going to have y squared times the derivative of e to the xy squared, and that again is the chain rule. And so we're going to end up with y squared times y squared, which is y to the fourth, e to the xy squared. All right, so negative y to the fourth, e to the xy squared. That's our derivative, our first second order partial fxx. All right, now let's look at fxy. So this means we're going to differentiate f sub x with respect to y. All right, so the derivative of sine y is cosine y. All right, and then we're going to subtract the derivative of the second term. Now notice the second term has two functions involving y multiplied together, so we're going to have to use the product rule here. Right? So our product rule with y squared and e to the xy squared. Right? So when we differentiate y squared, we get 2y multiplied by the other function. e to the xy squared. And then we add to that y squared times the derivative of the other function, which is going to be 2xy e to the xy squared. All right, and so this one, just right below this here, I'm going to rewrite this one. This is going to be cosine y minus 2y e to the xy squared minus 2xy cubed e to the xy squared. All right, so that one's a little bit more complicated, but still it's just really just Calc 1 derivatives with this understanding of how to compute a partial. Right? So now let's compute fyx. All right, so now we're going to turn our attention to f sub y and differentiate in terms of x. So the derivative of the first function is just 1 times the cosine of y. We're going to subtract from that the derivative of that second term, and that again we have a product of two functions involving x, so we're going to have to use the product rule. All right, so the derivative of 2xy is 2y, so it's going to be 2y times the exponential function, e to the xy squared. And then we have 2xy times the derivative of the exponential function with respect to x, which will be y squared times that exponential function. So again, I'll clean this one up a little bit. So we get cosine y minus 2y e to the xy squared minus 2xy cubed e to the xy squared. And our last partial is f sub y, y. So we differentiate that function with respect to y. Right? So in the first function, we have x times the derivative of cosine y, so that'll become negative x sine y. And then we have to, again, use the product rule because we have the product of two functions involving y. And so this would be 2x e to the xy squared plus 2xy times, if we're differentiating the y, it would be another 2xy e to the xy squared. Okay. And this one you can clean up if you want, but I'm not going to because A, I'm out of room, and 2, there was a particular reason I cleaned up the middle 2, and I'm not so worried about this third one. And so the reason I cleared up the middle 2 is that if you compare our cleaned up versions, these are exactly the same. Right, and we got them very differently. One, we took the derivative with respect to x and then differentiated with respect to y, and the other we differentiated with respect to y and then differentiated with respect to x. And there's no reason to expect that that would give us the same thing. There's many examples in math where doing things in different orders gives you different results. But in this particular example, these two mixed partials ended up being equal. So of course it's possible that this is just a coincidence, but since I've spent probably about 45 seconds talking about it, very likely it's not. And so we have something that we refer to today as Clairut's theorem, which says the following. Right, so we want to suppose that this this two-variable function f of xy is defined on a region. Right, so it's defined on some region in the plane that contains this point AB. And the real thing that we want to assume here is that f of xy and f of yx, these two mixed partials, are both continuous. At this point AB. So assuming that this function is defined in a region around this point and that the two functions are, or the two mixed partials are continuous, then the two partials at AB are going to equal each other. Right, so this is the result of Clairut's theorem. So this says that the result that we saw in the previous example where f sub xy and f sub yx were equal should have been expected. Right? That particular function that we had, it involved an exponential function, it involved a sine function, and just polynomials. Those functions are continuous everywhere. And so without really thinking about it, I know that the mixed partials were going to be continuous before I even compute them, because they're just going to be some algebraic combinations of sine, cosine, exponentials, and polynomials, and everything involved there will be continuous. And so this theorem tells me right away that once I computed the first mixed partial, I actually didn't have to compute the other one directly. I could just write down the same function because I know that's what I'm going to get. Right? Now, in the previous example, both of those mixed partials were, I would say, equally difficult to obtain. But the real strength of this theorem is that if we want one of the mixed partials and it's kind of complicated to compute, then we could also just compute the other one if it's easier, and that we know will have the same value. So for an example of what I'm talking about, let's consider this function. So let's let z be the function x cubed y plus y sine of y squared all over y squared plus 3. Right? And let's say we wanted to find the partial z sub yx. Right? So the definition of this partial derivative is that we have to differentiate z first with respect to y, and then differentiate that with respect to x. Right? And so if we think about doing it that particular way, first thing I want to do is differentiate this with respect to y. Now the x cubed y term is easy to do, but what we would have to then do is we'd have to differentiate this term with respect to y. Now it's not difficult. I mean, you all should be able to do it. It is a product and a quotient and a chain rule all combined together. It's kind of a very standard Calc 1 derivative that you might see. But it's going to be complicated. And so one thing we can do is we can realize that when we take the derivative of this with respect to any variable, we're going to get a continuous function. Right? The only problem we might have in this function with being not continuous is we could have a denominator equal to 0. But notice that the original function here, the only denominator is y squared plus 3, which is never equal to 0, at least for real numbers. And when we do the quotient rule over there, we're going to get y squared plus 3 quantity squared, which will still never be 0. And if we have to differentiate again, even, we're just going to keep getting powers of y squared plus 3 in that denominator. And so we never have any 0 denominators to worry about. And so we know the mixed partials are going to be continuous. Right? So when I look at this problem, mentally I realize that z sub y is complicated, but z sub x, the derivative with respect to x, is much simpler to compute. And since by Clairut's theorem, we know this is equal to zxy. Right? And so to compute this is much, much simpler. Z sub x is just 3x squared y. And then that second term, the one I boxed in red, is actually 0 because there's no x term. And then zxy is 3x squared. Right? And so by Clairut's theorem, zyx, the partial that we want, is 3x squared. We actually do not need to compute the derivative with respect to y. So let's look at an example with a function of 3 variables where we need to compute higher order derivatives. So let's let f of xyz be the function 2x cubed yz squared minus x sine of yz plus y to the fifth z. Right, so this is a function of three variables x, y, z. Let's say we wanted to compute and find the partial derivative f sub z x, y, z. Right, so in order to do this, we just simply need to take four partial derivatives with respect to the given variables in the particular order. So the first variable that we want to differentiate with respect to is z. So the first thing we're going to do is compute f sub z. And so the first term, we're differentiating z squared. So we're going to get 4x cubed yz. And then the second term, it's going to be negative xy. The y comes from the chain rule. Cosine of yz. And the third term is just y to the fifth, the coefficient of z. So f sub z is 4x cubed yz minus xy cosine yz plus y to the fifth. Right? We now need to differentiate this with respect to x to get f zx. Right? So to differentiate with respect to x, the first term becomes 12x squared yz. For the second term, we have x times a constant in terms of x. So this is just going to be minus y cosine of yz. And the derivative of y to the fifth is 0 with respect to x. So we just get 12x squared yz minus y cosine yz. Third step is to differentiate this with respect to y. So the first term, the coefficient of y there is 12x squared z. And the second term, we will need to use a product rule because we have y times cosine of yz. And so the derivative of y is 1. So we have subtract 1 cosine of yz. And then I'm going to go ahead and distribute that negative across the product rule. And so we're going to have y times the derivative of cosine yz. And that derivative is z times negative sine of yz. And so that negative there makes this term a positive. And so I get 12x squared z minus cosine yz plus yz sine yz. Okay. And then the last step is to differentiate this one last time now with respect to z. Okay. So the first term, we're going to get 12x squared. The next term, it will become positive y sine yz. Right, so it becomes positive because the derivative of cosine is negative sine, and the y is part of the chain rule. And then this last term, we will need to use the product rule. So the derivative of yz is y times sine of yz. Plus yz cosine yz multiplied by another y, so I'll make that y squared z cosine yz. And so if you want to try, I'd really encourage you to try this for the same function f. Try to compute the derivative f of yxzz. All right, so it's still a fourth order partial derivative, just in a different one. And if you do it correctly, you should get the exact same function that I just did in my example. Right? And if that surprises you, you can look at the variables that we're differentiating with respect to and notice that although they're in a different order, we're differentiating with respect to z twice, x once, and y once. And so what we can, this doesn't obviously prove anything, but it does at least suggest that what I'm about to say is true. And so Clairut's theorem that we just talked about in terms of mixed partial orders for second order partial derivatives. This holds for mixed derivatives of any order. As long as the partial derivatives of that particular order are continuous. And so for this particular function, again, we look across, it's a polynomial, there's a sine function, but this function is going to be continuous everywhere, and every derivative of it, regardless of which variable you differentiate with respect to, and regardless of how many variables and what order you differentiate them in, every derivative of this is going to be continuous as well. And so Clairut's theorem applies and says that if I differentiate with respect to x once, y once, and z twice in whatever order, we're going to get the same exact function. All right, so in this example, we started with the partial f sub zx yz, and you showed that f y x zz is exactly the same. And so by Clairut's theorem, as long as we take the fourth partial and we have 2 with respect to z, 1 with x, 1 with y, we will get the same function. So if I did f sub y zzx or f zx zy, these are all going to equal each other. And so if the functions are continuous, this is really, really nice because we don't have to compute as much as we might think we have to. Okay. The other benefit, of course, is that if we want to compute a particular partial, we can try to find a term that is easiest to compute. Right? So for example, if this given function on the screen right now, with this f of x, y, z, the first thing I might do is differentiate with respect to x, because the first 2 terms are quite easily differentiated with respect to x, and the third term will become 0. Right? And so then once I write that down, I know I'd have to differentiate with respect to y once and z twice, and so I could decide whether I want to differentiate with respect to y or z next in order to make the simplest derivative. And then continuing like that until we've differentiated with respect to all 4 of the required variables.